Session right now on the schedule, it says there's going to be an hour of lecture and then an hour and a half of hands-on. The lecture is actually going to be much shorter than that, but similar to Monday, there's a problem I want to go through with everyone at the beginning of the notebook, so we'll do that. And then we'll take the break, and then we'll go to work on the notebook. All right. So I was thinking about it last night, and I wasn't sure if this talk comes out of order or precisely in the right order in context with everything else that we've done this week. My basic idea is that we've worked on many problems, we've talked about several different algorithms, but we have not yet had a chance to sort of really look at if I'm dealing with actual real data, instead of like the IRIS data set or the MNIST data set, which is real data and is a hard problem. But if I'm dealing with actual astronomical data that has all the quirks that our astronomical data has, what are the things I need to think about if I'm actually going to build a machine learning model? So that's essentially what this talk is about. And then some of the notebook, you'll notice, is similar to some things that we did on Tuesday, in part because parts of it were borrowed for the How to Interpret a Machine Learning Model lecture. Also, because this talk is short and because we're at the end of the week, and this is about the practical applications of machine learning to astronomical data, I want you to stop me in the middle of the talk and ask questions if you have the questions, okay? This can be much closer to a dialogue than an actual lecture. I don't want to just spout things at you for the next 20 minutes or so. Okay, a lot of what I'm pulling from this lecture, a lot of the slides that you're going to see are taken from this book, which is a very approachable introduction to machine learning. So many of the books that you'll find on machine learning really go into depth on the algorithms that you'll be using, the backbone of the mathematics of what's going on. This book was written by Henrik Brink and Joey Richards, who are essentially the two people that I learned machine learning from. They were in my group at UC Berkeley when I started working on this kind of stuff. They talk a little bit about algorithms, but essentially all of it is just practical advice for building a machine learning model using actual data. Okay? And so from there, I'm going to start with the figure that they repeat again and again and again throughout their book, which is the machine learning workflow. All right? So the first step is you have some historical data or training data. Laser pointer is dead. You have some historical data or training data, right? This is how we're going to build our model. We've seen this many times. And then the actual modeling steps, because we haven't talked about this much, because for the most part, we've had toad problems where you apply the algorithm that we give you and you get a more or less good answer. But the actual modeling steps involve building a model, evaluating the model, optimizing the model, right? So model building, that just means essentially selecting an algorithm. Evaluation, cross-validation is one way to do that. You may have some other metric that you're hoping to maximize. Model optimization is the process of basically going through your model tuning parameters and making sure those are the best to give you the results you want. And then you'll notice that this is essentially a circular pattern. Okay, so in real life, these things, you do one of these things, then you do the other, then you do the other, and typically you have to play around with that and iterate, right, in this procedure several times before you actually arrive at a model that you're happy with, right? And then eventually at the end, you make predictions on your new data, right? This is the ultimate goal. Now, for many real-world problems, you can make those predictions, and then you can immediately get answers as well, right? If you're trying to build a model that predicts whether or not someone's going to click on an ad, you will also have a data point telling you that they did or did not click on the ad, right? And so it's easy to essentially get more data, and you can feed that back into your model. You can essentially retrain. In astronomy, you can do the same thing, right? You can make a bunch of predictions, you could go out and take some spectra. But typically, the feedback process in astronomy is much more expensive, right? You have to go to ATT&CK, you have to get approved. Most of the time you won't, especially if you're just trying to, say, verify a machine learning model by using some big piece of glass or big radio telescope. So this last step can be really hard for astronomers. Okay. All right, so data preparation. We actually haven't talked about this. Some of these ideas we've touched on briefly throughout the week. So I just want to go through sort of the flow of everything you need to consider as you're getting ready to actually feed your data into a model. And some of these steps I'll also note, if you want to use the latest and greatest and actually build different types of neural nets along the lines of what we learned about yesterday, you may not have to do so much of this because essentially the algorithm can take care of some of this. But if you're using sort of more classical, if you will, machine learning methods like random forest or k-nearest neighbors or the different unsupervised techniques that we learned about, these are steps that you have to go through. All right, so the very first step is to essentially grab the data that you want to model. That can either be from a query if it already exists in a catalog, or maybe you have to go to a telescope and actually make some observations, or you can also simulate the data. Right? That's another way. So that's step one, is to get the data. All right, and then you have to worry about the data. You have to really, 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 really worry about the data. Right? Because almost every single way that we get our data is biased. Right? And if we want to propagate some biased subsample of our data to predict on some larger on the full set of data or the large set of data that we have to understand those biases. So I spend most of my time, if I'm building machine learning models, worrying about the data. Far less than I do actually messing around with the algorithms. All right. Then we need to select the few features that we want to use in the model. Again, if you're doing something like latest and greatest neural nets, you don't actually have to select the features. The algorithm itself will figure that out. But in many cases, this is something that you actually have to do yourself. And questions you need to ask here are, do I have enough features? Do I have the right features? Do I need new features? Okay. Determine ground truth, or the labels for your training set. Right? Again, this can be very costly. If you need to actually take a spectrum of something to get ground truth, that's expensive. Right? Spectra are expensive. If you need to, even if you just need to look at something, right? If you can take a light curve and look at it and classify the source, that is also an expensive operation. That doesn't happen quickly. So that's an expensive step. Sometimes if you're pulling everything from a catalog, right, you can do all of this just right away with your query. So if someone's already done the work, it's maybe not expensive. But typically that's an expensive step. Categorical features is something that I don't think has come up once this entire week. Right, it's perfectly valid to, say, keep track of gender or something similar while building a machine learning model. But you can't just directly necessarily convert, say, male, female, or transgender to, right, 1, 2, 3, because if you change those variables to 1, 2, 3, you've now imposed an order on the data, right? And if you're using sort of standard Euclidean metrics to measure distances between sources, you've now moved, right, you've moved one of your categories further away from the other, even though there's no physical relationship there. So the standard typical transform for categorical features is just to create binary, right? So this flowchart shows the procedure, but to create binary variables for each of your categories, right? So either you belong to the category or you don't, right? And that way you don't impose structure on the data that isn't necessarily physically there. Yeah?
But what if you have multiple categories, right? So there's only 2 here.
Every category gets its own feature, binary feature, on or off, essentially. Okay, right? So this, I mean, this could be hair color.
Yes, got it.
There could be 20 features, and then it's red hair, blonde hair, purple hair, etc. Okay. All right. Another idea we haven't talked about much is missing data. All right. A lot of times, data is missing for some reason, right? You maybe for some objects can measure 10 of the 12 features you care about, but 2 of them you don't have measurements for. And that can be for a variety of reasons. The most common, I would say, in our field is that a source is too faint, say, in a particular passband, right? So if you care about M-dwarf stars, you maybe don't have U-band measurements from the Sloan Digital Sky Survey. If you care about white dwarfs, you maybe don't have Z-band measurements from the Sloan Digital Sky Survey, right? So what do you do there? Here's a sort of workflow for things you can do if you have missing data in your training set. So the first question to ask is, does the missing data have meaning, right? So the 2 examples I just gave, the missing data actually is meaningful, right? A M-dwarf star that isn't detected in the U-band is faint in the U-band. That means something. We don't know how bright it is, but that does mean something. In other cases, the missing data can not have meaning in the sense that just for some reason a particular observation didn't happen, right? So you can't actually infer anything from the fact that it's missing. So if there is meaning, you can essentially just replace the value with some numerical value. You could pick -99. You could pick -99999. Right? You do have to think a little bit about what numerical value you choose. depending on the algorithm you're using, or you can just create a new categorical variable, right? That's just missing data or not missing data. All right, but if it doesn't have meaning, say just for whatever reason that particular patch of the sky wasn't observed with the telescope that gave you the feature that you have for much of your other data, then there's a sort of flow of questions you can ask yourself in terms of what you should do. So if you have a very large data set and there's very few missing values, the easiest and probably safest thing to do is just remove everything with missing data. If you're throwing away a very small fraction of data from a large data set, that's not a big deal. Probably won't bias you. Again, because in this case we're saying that the missing values don't have meaning. All right, if you have a large temporal data set, so some time series and you have some values that are missing for whatever reason, you can just use the preceding value in the time series, or you can even interpolate from the preceding to the post value, the missing value. You can fill in the missing data that way. If your data set has a very simple distribution, right? If it's just some Gaussian distribution, you can just replace missing values with the mean. Right? If you have a slightly more complicated distribution, you have some outliers, maybe use the median instead of the mean. Right? Finally, if none of those things are true, right? If you don't satisfy any of those conditions, it may be that the best thing to do is actually to build an entirely separate machine learning model to predict the missing values. Right? This is something that's fairly common. I've done that before. You can use any type of sort of regression methods to use the features that you do have information for to build a model to predict the missing features. All right? And you do all this with your training set. Yeah, question?
So on the one where it places missing values with mean or median,
yes.
Wouldn't that create an artifact where there's a huge spike in the middle that's not there now?
Okay, so if you were getting a huge spike in the middle, that would suggest that most of your data has missing values.
Yeah.
In that scenario, I think the practical suggestion would be to just create, probably to create a new categorical variable.
Okay.
Okay.
But it's a problem even if there's a small amount of data missing, right? There's still.
So the distribution of the data is not going to change much if you're adding values at the mean.
It'll artificially lower the standard deviation.
That is true. Yeah. Look, so all of these things, right? You have to be right. All of this is taken into consideration, which I'll talk about in a second, with the particular algorithm that you're using, right? And how it's going to deal with this. In some cases, this may be a terrible strategy. For other algorithms, it's not such a big deal. So, for instance, I would tell you if you're using a random forest algorithm, which is very nice for many astronomical applications, changing that distribution won't matter so much because all you're doing is you're branching by split points in your data. Okay. So the actual distribution doesn't have a huge effect on the final model that you have. Is there another question now?
I was just thinking if the algorithm allows for it, could you also handle it by putting some value but then also much lower weight?
Yeah, absolutely. Yeah. Yes.
So in the first scenario, we have so many numerical values to feed in, like for example, -999, or maybe not a number, or maybe NumPy infinite. So what do you think, like in which kind of situation we should use what kind of strategy?
That's a good question. That is also going to be, I think, an algorithmic dependent question. So again, if you're using some sort of decision trees to build your model, right? You just end up splitting on some point. So if you go to infinity or you go to negative infinity and you're splitting at 5, it doesn't matter if it's -999 or negative infinity. If you're building distance measurements to like a k-nearest neighbors to do your classification, then you want to be careful about how large you make those numbers, because all of a sudden you're now essentially placing sources infinitely far away from the rest of your training set. So it all comes back to what is the algorithm that you're using. Okay. All right. Not all algorithms require this, right? And we've talked about this briefly, but not much. But sometimes you need to normalize the features, right? Did anyone actually get a chance? Did anyone look at how the results changed for the iris data set if you normalize the features versus not normalizing the features? Can someone give me some intuition for what might change if you normalize the features? Nick?
The features that are measured on sort of different natural length scales will dominate the separations less, so you get a more uniform mixing of features.
Right. Right. So again, when we were classifying the iris data set, we were using k-nearest neighbors, which is just measuring Euclidean distances. So if you have one feature that's just naturally larger numbers, even if that doesn't necessarily help you classify any better, that feature will dominate the classification that you perform. Oh, actually, you know where we did see this? Sorry, I'm just remembering. When we were looking at the classifications that happen if you use the U minus G color and you haven't normalized the feature. This was actually in the unsupervised notebook that we did, right? But U minus G is typically, for most sources, a much larger number than, say, G minus R color or I minus Z color. And so the classifications, when the features were not normalized, essentially were just giving you what is U minus G. And then once you normalized all the features, right, we saw that their classifications did not have the sort of simple horizontal separation that they did before the normalization. So again, algorithmic dependent. Not all algorithms require this, but some do. And then finally, right, always visualize the data. Right, it's good to look at the data, make sure things more or less appear as you might expect them to. Right, we don't want to just be pulling stuff in from a database, never looking at it, building models, and assuming that the output is good. Right, this is a very good step for understanding what's going on with your data. Okay, and then even after you've done all that, you should worry about the data. All right, can't emphasize this enough. You should always be very worried about the data. Okay, something that we briefly touched on earlier in the week, but I think is very important for our applications is feature engineering. All right, some of this is done algorithmically. Some of this is by using the fact that you actually are an astronomer with some intuition for what is physically going on in the universe. All right, so that's what we refer to as domain knowledge in machine learning. Right, we're not pure statisticians. We actually have some expectations for how our data might be modeled by the various features that we have. All right, so essentially in feature engineering, there's more or less two things you can do. You can add new features, all right, which may be a necessary step, utilizing your domain knowledge to create something new. Or maybe you need to combine your features or represent them in an alternative fashion. So I think a good example there is, suppose you're building an online model, again, to predict whether or not someone's going to click on an ad, and you have the location of every person in your model because you have their IP address, right? A raw location may not be very helpful or very predictive in whether or not someone's going to click on it, but maybe you could use that location to convert a new feature that's population density, right? Because maybe people in Los Angeles, Chicago, New York are more likely to click on an ad than someone, say, living in Montana. Maybe, maybe not, I don't know, right? But that's an example of feature engineering, and it can yield huge improvements to your model, right, when done properly. More sort of on the algorithmic side, you can remove noisy features or uninformative features. You may or not need to do this. Luckily, the cap was on there. All right, whoops. Sorry. Where were we? Here we were, sorry. Right, so random forest actually has a measure a way of determining the importance of each feature. Right? Essentially, by examining the trees and what would happen if you randomly shuffled the values of each feature, how much worse is the performance of the model? That's how that's happening, and we'll do an example of this later. Here's a plot just showing an example of that, right? And just by looking at this plot, it's pretty clear that most of the power of this classifier is in the first 4 or 5 features. Right? There's not a whole lot of extra information coming from the additional features. That doesn't mean there's no information, but there are cases where there's thousands or even millions of features for models. That doesn't typically happen with astronomical data, but in that scenario, there's a good chance that you'll have to actually get rid of some of those features or do some kind of dimensionality reduction. And then another thing that we heard about, but I have a picture of it over here, is forward or backward feature selection. Right, so this is where you take all the features, you build a model using only one feature, see which feature is the best. Okay, that feature gets added to the model. Right, and then you do the same thing using the feature you already selected, iterating over all the remaining features. And you look at the performance of the model, how it changes as you keep adding features. So here's a plot from a paper by Henrik. So each one of these lines, don't worry about reading them, is a different feature. All right, and basically they're looking at the miss detection rate, how many of the things they care about are being missed. And good is moving towards me, right? Good is moving this way. So when you start with a small number of features, the performance is not particularly good. As you add more features, the performance gets better until eventually the noise starts to dominate, right? And so the performance gets worse. So you can do this forwards or backwards. And in this way, you can sort of figure out what is the optimal number of features from the model.
But I guess the order of those features would also matter.
So that is, right. So Daniela mentioned you can do an exhaustive search, which is that you look at every possible combination of features, which is a number that is too big to explore, typically. Even doing the search in this way is, requires 2 to the n models. And so it's possible, right? It's possible there could be some correlation that the model finds between 2 features that if you're working in an iterative, 1 feature at a time situation, you don't properly identify. Yeah. So you may miss out on something by doing this, but it also may be necessary if you have way too many features and your model is just noisy. Okay. Ashish?
The comment that I made, I'll make again that this may be very dependent on what it is that you're trying to separate, because some of the features that are right there in the tail may become important for some specific sub-question that you may want to ask. So generically, yes, you can do something like this, but then if you change your question especially, then you will have to revisit that.
Yes, right. Yeah. Okay. All right, so what's next? Model selection. So here, similar to the rogues gallery of unsupervised methods that I showed on day 1, here's a rogues gallery of some supervised methods for classification. So each row here is a slightly different problem. These are all 2-class problems, right? And then the predictions, right, from some different algorithms that we've seen this week, nearest neighbors, decision trees, random forest, neural nets, right? Predictions from these models are shown in each of the columns here, right? And so the algorithm affects the final results, right? This is the same data set for each of these algorithms, but the predictions that you get out look very different, right? So choosing the algorithm is actually a very important step. And after you choose whatever algorithm you're using, you should worry about the data. Only 2 people think that's funny. That's fine. It's true, you should worry about the data. All right, so after you choose your algorithm, you want to evaluate your data. A big part of the reason why we do this is we want to avoid underfitting or overfitting, which Daniela told us about on day 2. One of the best ways to do this, right, because we don't want to snoop on our test set, is to use some form of cross-validation. Here's a figure from day 1 showing k-fold cross-validation. Alternatively, you may not be trying to just, say, maximize the accuracy of your model. Maybe there are specific classes you care about more than others. So perhaps you evaluate using something like a confusion matrix or an ROC curve. Right? But this is part of that loop of model selection, model building, model evaluation, and model optimization. Okay. Model optimization, typically, this is just as we saw briefly in Tuesday's exercise. Typically, model optimization is just done via grid search. Okay, so all the tuning parameters I have for my model, I'm just going to create some grid and search over that grid to try to find the best combination of parameters. Here's an example from for an SVM model, support vector machines, which has 2 parameters, a penalty parameter C, and essentially a regularization kernel coefficient gamma. And you'll notice in this particular grid search, the penalty parameter C does not have a strong effect on the output of the model, but gamma has a strong effect, right? So choosing gamma correctly here will significantly influence the results that you get. Right? If your grid is very, very large, like if there's many, many, many tuning parameters, there are alternative methods you can use which don't actually search every single point on the grid to try to get close, right? It's not necessarily guaranteed that you'll be right at the optimal choice for the model, but you can get very close this way. Right? And finally, model prediction, right? And we've seen this a few times throughout the week, but at the very end of the day, right, what we want to do is take some data that does not actually have labels and make some predictions on that data. Here's just an example from the neural net problem that you worked on yesterday. Okay? And then, right, all right, so now that you have your predictions, you're ready to write a paper, so you should worry about the data. Yes, that's right. Okay. Always, always, always worry about the data. Okay, so again, just to review, this is the same figure I showed at the beginning, right? We start with our historical data. In many cases, we have to massage that in many ways if we want to pass it into a machine learning algorithm. From there, we build a model, evaluate it, optimize it, and possibly do that several times before we get results that we are happy with, and then we can make predictions on our new data. All right? So I'm going to stop here and ask if there are any questions. All right, if you haven't already, you should do a git pull, and we'll pull up the notebook, and it's going to look very familiar. We're going to be doing an extended version of the classification of stars and galaxies in Slum data, a problem that you guys will know so well by the end of today. I'll wait till your eyes are up on me before you start moving here. So if you executed the git pull, eyes up, please. Yeah, Lee?
Just a question related to before. I could understand the idea of like worrying about the data at every step of the process, but after predictions specifically, like what are you looking for in terms of something that might make your model fail on the data or
I mean, to some degree, you just you can inspect the predictions and evaluate if they are in any way in line with expectation. So for instance, that to zeroth order, if you're building a model that predicts photometric redshifts, and your model tells you that there's a spike of galaxies at redshift 2, which could happen. It's worthwhile saying, okay, is that physically plausible, right? And I think that is the question that I find myself asking at the end of the prediction stage, right? Are these results physically plausible? And a lot of times, if there are biases in the data, it's possible to sort of tease that out by just looking at the sort of whole suite of predictions. Okay, and then if they're not physically plausible, it probably means there's an issue upstream. Okay, yeah. All right, so I think everybody's up and running, or if not, very close based on the eyes that were up on me. So, right, this is a problem we've looked at a few times. There's some text in here that's new, but the first part is going to look very familiar. Okay, so just a quick reminder, right? The flow that we just talked about was data preparation, model building, model evaluation, model optimization, followed by model predictions. Okay, and we're going to do each of these things. We don't have time. I didn't have time to sort of arrange the data in a way that these steps have to be iterated, all right? So things are just going to work out your first time through. It's not going to be as headache-inducing as this would actually be in real life. But we're going to go through each of these steps, okay? Just quickly, I don't know how much we've talked about this, but just for some science background, I think you could probably make a pretty good argument that everything that we will do with LSST will come down to our ability to separate stars and galaxies. You know, just as a quick example, imagine if you're trying to measure galaxy clustering, but you don't know if that faint red thing on your image is an M dwarf or a galaxy. Right? It would totally mess up your statistics. So this is a really important problem, even though in many cases it seems like you can arrive at an answer relatively easily. Okay, so we're going to use supervised machine learning to look at galaxies and stars and quasars. Yeah, okay. All right, so the first step is to obtain and examine the training data. Right, so problem one here, this is going to look very, very familiar at this stage because it is, I think, more or less identical to what we did on Tuesday. All right, so we're going to use Sloan data. We're going to get 8 magnitude features. One thing to note is that if you wanted to throw all of Sloan into your model, there's actually 454 columns for the photometric database. Okay, so you could have many, many more features than just the R-band magnitudes. We're keeping it bite-sized now so we can visualize it, but you could do that. Okay. All right, so the first step is to prepare the data. So we're going to curate the training set. We're lucky here, Sloan has done all of the hard work. They have both imaged more or less all of the northern hemisphere and also taken spectra of millions and millions of sources. All right. So another thing, I should have emphasized this more in my talk earlier. Right, the model is only as good as its training set. This is true of all machine learning models. Right, even if you're doing the fancy latest and greatest neural network stuff, you give it a bunch of crappy images, it's not going to be able to tell you the difference between a dog and a cat. Okay. All right. So yeah, we don't have a good training set. We're not going to have a good model. All right. 2 very important things for the training set is that it should be unbiased. Right? We talked about this already. This is really hard to do in astronomy because essentially any survey that you do is magnitude limited. Right? Magnitude limited means I can only detect objects up to a certain magnitude, which means I'm only sensitive to objects out to a certain volume. Right? You get a telescope that can go deeper, can go to a fainter magnitude. Now your volume's larger, and the statistics of the population that you detect is probably different. And then hopefully the training set will be ideal of the population of sources that you're trying to classify. Okay. And again, this is very hard to achieve in astronomy. As an example, right, if you had a training set that's all galaxies, there's no way you could possibly find a star. Okay. All right. Okay. So we're just going to grab the data and visualize it. All right. So let's execute the first few cells in the notebook. This is going to look very familiar, but there's one question I'm going to ask you that I don't know that has been asked previously this week. All right, so we can grab that from SPSS. Just a little background, right? Here's how you can quickly get all of the R-band magnitude measurements, right? Instead of actually going to the list of 484 things and trying to identify everything in R-band, you can actually query the database to get the columns that look like the thing you want. All right. Speeds things up a little bit. We're going to grab 10,000 stars, just as we did before. Okay, just some quick background on the Sloan database. So some of the conditions we put on the query are that mode equals 1. So this ensures that if an object has been imaged twice, say because there's image overlap, we only get the primary photometric detection of the source. So we don't want repeats in our training set. And then when we're grabbing the spectra, which we're going to use to label the sources, we do the same thing. We only want the primary spectrum because several sources were actually observed multiple times with the spectrograph. We're going to make life a lot easier by setting the clean flag on the photometric detections to 1. All right, so this ensures that we're only getting essentially clean photometric measurements. So there's all kinds of photometric measurements that have problems. There are things like cosmic rays. Sometimes a star falls on the edge of your detector, so you don't have the full PSF. Same thing for galaxies. Saturation for bright stars, right? All of those things are getting thrown out. Right? So that's helping us in the data preparation process. And then finally, as the last step, we're not going to include quasars in the training set, although at the very end of the notebook, we're going to try to classify quasars. Right? And we'll see why quasars are maybe a little difficult to build a model on. Okay, so I'd like everyone, if you haven't already, to execute the query. And this will look very similar to, possibly even identical to what you had on on Tuesday. Okay. All right, so data-driven models are only as good as the training set. So the first question is, can you easily identify any important properties of the data from the above table? Emphasis on easy, and if not, is there a better way to examine the data? You can either type the answer in the solution cell that's right below, or talk to your neighbor. We'll spend only a minute on this. All right, it's been about a minute. So let me ask, can you easily identify anything from the table itself? I see most people shaking their heads no. All right, I contend that you guys are ignoring your domain knowledge. Eve, yes.
Based on this limited number of data points that we can see here, it seems that there are a lot more galaxies than stars.
Oh, okay, yes. And so that is going to be a magnitude-dependent question, more galaxies than stars. I think Sloan is sort of right at the cutoff. So Sloan goes down to about 21.5 magnitude. And in the Sloan database, the numbers are actually about comparable. We'll look at that in a second. The training set, I do believe, is biased, though, to have more of one than the other. So the domain knowledge that I was thinking of is that point spread function is a terrible way to model a galaxy. Right? This is domain knowledge. I don't know that a non-expert looking at the table could quickly pick this out. But right, we know that point spread function is terrible at modeling a galaxy. And if you look at a few of the columns, you can pick any of them for galaxies, and you compare some of the essentially methods designed to measure galaxy brightness, and you compare them to the point spread function magnitude, right? There's a significant difference between those, right? Now let's do this the easy way, right? Which is to visualize the data, which I think I heard most of you bring up. So visualize the 8-dimensional feature set, right? This should be fairly quick. Right, here's a question. Can you identify any biases in the training set? So after you do the visualization, I want you to really think about this question, right? This is what most of my talk was about this morning. Worry about the data. So try to find any biases in the training set after you visualize the data. Okay? Oh, yes, thank you. if you need a hint for visualizing the data, the solution that you came up with on Tuesday during the interpretability exercise should suit you just fine. Once you have the plot, talk with your neighbor to see if you can identify any biases.
Maybe a lot of these are noise. Yeah, I mean, some of these things are, 20 seconds. Such a very straight light problem.
We can look at that later. I'm not sure, but I'm not sure I'll we'll be able to figure this out in just 30 seconds. Yeah. Okay, so I see most people have the data visualized.
It's true, this is image. If that's what it means. You know what all these columns are?
All right, so let me ask, did anyone come up with a potential bias in the data set?
Looks like intermediate brightnesses are missing.
Say that one more time?
Looks like intermediate brightnesses are missing.
Intermediate brightnesses are missing. Yeah, that's great. So I think that's the one that's really clear from the data set. So ask you to complete this problem, right? So we can do this using a Seaborn pair plot, which is something we've seen a few times this week. And you'll notice, right, along the diagonal, so those are, I think it's a little easier to see if you actually do a kernel density estimate as opposed to a histogram, right? But you notice the distribution for both stars and galaxies peaks up around 18th magnitude or so, and then there's a dip, and then there's another peak after that, right? We know physically that is not how the universe actually is, so that means there's some bias. Just out of curiosity, does anyone have a guess why that bias is there?
The giant stars are short-lived.
No, it doesn't have to do with it does not have to do with populations actually. So this bias exists because the folks that ran Sloan wanted a complete galaxy catalog down to about 18th magnitude. Okay. So if it was kind of extended and greater than 18th magnitude, it took a spectrum. And then the secondary peak that you see there, that is for measurements of baryon acoustic oscillations. Okay, so if you want to measure baryon acoustic oscillations at a redshift order 0.5, you need to take a lot of spectra of red galaxies at about 21st magnitude. Okay? So that's where both of these spikes are coming from. They have nothing to do with, it's not a problem with the data, right? This is a problem with a decision that some other astronomer made. Okay? But again, these kind of biases come into the data all the time, right? Every observation that an astronomer makes is a biased observation because you're pointing the telescope somewhere and not somewhere else. Okay? So these are things we got to look out for. They're things we should be really nervous about if we're building machine learning models.
What are all the columns? I wasn't paying attention. Are those colors and magnitude?
These are the magnitudes of stars and galaxies in the 8 different R-band measurements that Sloan makes. Which it's too small to read here, but PSF mag, fiber mag, Debockel's profile, model mag, etc. Debockel's magnitude, excuse me. Okay.
Why are the R-band magnitudes it measures for stars so much more consistent than the R-band magnitudes that it measures for galaxies?
Sorry, say that one more time.
So these are all measurements of the same thing, right? R-band magnitude, but in different ways.
Yes. Yes.
So it looks like the measurements for stars are much more consistent between these different methods than for galaxies, in the sense that there's much more scatter in the galaxies.
Right. So the reason you see the additional scatter in the galaxies is what we talked about a second ago, which is that a point spread function is a terrible model for a galaxy. So if you fit a point spread function model to a galaxy, you will systematically underestimate the noise. And essentially our models are going to use that fact to separate these two classes. Yeah?
Shouldn't it also have to do with that all stars look the same, but all galaxies have different morphology? So if all galaxies look the same, then wouldn't the galaxies also share this very narrow feature, or a very narrow distribution across?
So variations in the actual shape and brightness profile of the galaxies is part of what is giving rise to the larger scatter than you see for stars. Yeah. All right. Okay. All right. We have a few more minutes. This is what we said, right? There was a dip at about 19th magnitude. We now understand why that dip is there. It's because of the way that Sloan was targeting sources for spectroscopic observations. Okay, so now we want to finish off our preparation of the data. So we want to create an independent test set. So we're now going to divide the data. We're going to take a test set that's going to sit aside for the whole rest of the project until it's time to evaluate how good our model is. Right? And in this case, we want to do a 70-30 split. Again, this is very similar to something we did on Tuesday. So here's the problem. Using train test split, right? Split the data so that you have train X, train Y, test X, test Y, right? With 70% of the data going into the training set and 30% going into the test set. Okay? And I even think there's a few hints there for you. And again, this should look very similar to what you did on Tuesday. So if you need a refresher, you can go back there, or you can raise your hand. I'll help you out. I'll also remind you that typically everything in my notebooks is linked, so you can click on test train split where I first introduce it, and that'll take you directly to the docs. You can do that, refer that to using Google. Also note that typically at the end of the docs there are examples for how to use different functions in scikit-learn. So if you don't recall what the proper syntax is for train test split, you can go to the docs and scroll to the bottom. See an example that should be helpful. You don't need to do that matrix. And you're fine, actually. I think you need an in place. It's not, because it's not pandas drop, it's an attribute of the data frame object. You might need an access call. Yes, and I think that also might be a pandas dependent, pandas version dependent solution. All right, so as this is something that we've already seen, I'm going to put the solutions up, all right, or at least my version of the solutions. Okay, so there's multiple ways to do this. You do need to have this done, so I'll leave this up for a second if you need to copy it down. But I created a list, which is the name of all the features, since you can index pandas data frames very easily based on the column names. And then I removed from that list the class, right? That's going to be our target variable, so I removed that from the list. And so then I just set x equal to a numpy array of the SPSS set, selecting only the columns in our features list. And I had to convert that to pandas in order to convert that to a numpy array. And then for y, I just selected the class from SPSS set. That's my y array. And then using the syntax that we already have, train x, test x, train y, test y, equals train test split x, y, and then we set test size equal to 0.3, and the random state equal to rs. Okay, I'm going to leave this up for just another second. Yeah.
What was the random state?
So are you asking what that means, or are you asking what the number is?
Yeah, what
Essentially, we're using a random number generator to split the data into 70-30 chunk. and we when you're doing that random split, you can actually set the value of the random state so that we all have the same random split. Okay, so by setting the random state equal to RS, every single one of us is going to get the same random 70-30 split. This is a useful tool for that particular reason in the classroom, but it's also useful if you're, say, building pipeline and you want to compare different versions of your pipeline. Then this ensures that you have the same random, same random separation of your data in your different versions of the pipeline, and that you don't, say, change your pipeline, see a huge improvement, but it turns out that's just because you had a different random set. All right. Shake your head no if you don't want me to move on from this yet. All right, so I'll assume everyone now has the training set and the test set on their machines. Okay. All right, so this is the problem I really want to get to. So we're going to break a little bit later than the schedule says at 10, because I want to do this together. And then if you want, we can split up after the break for the rest of the notebook. Okay, so feature engineering. Something that if you're using fancy deep networks, fancy new versions of neural networks, something that you maybe don't even have to worry about, because the algorithm itself can take care of this. But for many, many problems, something that you have to deeply, deeply, deeply care about, think about, and work hard at. I introduced this briefly in the talk, all right? Sometimes you have to adjust your data, adjust the features you're giving your model to get the results that you want. All right. We're going to actually create a separate toy problem for this introduction to feature engineering, for the simple reason that there's some quirks in the training set that we have right now, and I had to create this toy problem in order to demonstrate the importance of feature engineering. In brief, we're going to run two queries, just like the one we just did, to select data from Sloan. The difference is going to be that we're going to have a training set that is only bright objects, so only things that are brighter than 18th½ magnitude, and then we're going to have a test set that's only faint objects, things that are fainter than 19th½ magnitude. Right? And we're going to see if we can use feature engineering to actually use these bright things, which maybe look totally different from the faint things, with our nearest neighbor model. As an aside to our quick aside on feature engineering, all right, this happens in astronomy all the time, right? We've talked about this already today, but this is the exact thing that happens in astronomy all the time. You build a bigger telescope, all of a sudden you have a lot of data of fainter objects that don't look anything like the objects you've known and studied and cared about for years, okay? In this particular problem, this is what's called sample selection bias, right? Almost any time you want to be building a machine learning model in astronomy, you're likely going to be dealing with this, okay? All right, so we train and test the model with 10,000 sources. We're doing the exact same query we had above, all right? The only thing that's changed is we're adding a selection of only the bright sources for the training set and only the faint sources for the test set. So if everyone could please execute this cell now. All right, and these data look more or less exactly the same to the training set that we have. What was that? To the training set that we have, except again, these are the bright sources. All right. Please execute the following cell as well, which is for the faint sources. All right, so now we have a bright set and a faint set. And the bright set's what we're going to use to train, and the faint set is what we're going to use to test the model. Okay? All right, so the next problem, train a k nearest neighbors model. All right, we did this on Monday if you need to go back for a hint on how you actually do that. 11 neighbors on the 10,000 source training set. All right. And just as a quick aside, the number of neighbors is not hugely important to this particular problem. I just happened to pick 11. Okay? So here's a prompt to get you started, and I'll walk around and answer questions as you have them. So this is going to look, so basically k-name is classified. That's the conservative model. So you've got that exported. So essentially now we just want to create an x and y array from the bright set that we can use to train the model.
way that will be calling the models very similar to everything else we've done. So it'll be the inverse classifier and underscore equal equal like then dot and then dot. That sort of thing. Okay. Okay.
If you're wondering how to get the data into an X and Y array, it's the same procedure we did above, right? So we have an AstroPy table.
Just for this, just like the label?
Yeah, just the label.
And,
It's like later.
so
Giving
this-
you a there. Oh, and also it's you don't throw the results basically
So we're just trying to fit the model right now. Right, yeah, you're training on the entire right set. We're not doing any sort of split right here. We're going to train on all 10,000 sources. So I see that some people have already moved on, so can I see a show of hands, or can you keep working, that's fine. If you're still on 2A at the moment, can you just look up at me? Okay, thanks.
So, because your great X role is long. Oh.
Yeah, that's fine. We just want to set the number of years.
Nothing is actually returned. It becomes an attribute of the Python object. You don't need to set right set or you just call KNN.
All right, so I think everyone has the model fit this stage. All right, so the next problem, which I saw many of you have already moved on to, is to evaluate the accuracy of the model. And then I ask, does it perform well? Okay. So very similar to what was done in the cell before, we're going to convert the data into X and Y arrays, and then measure the accuracy of the model. Yeah.
Down by about 35%.
Yeah. You should look at what you're predicting on. It says.
Oh. Somehow I get only an improvement of 20% accuracy. And
There's-
you get 35%.
There's some randomness. It may not be exactly the same. Yeah.
Predicting on the thing. Right. What do you want to do? Yeah, but what if you normalize the thing? So you said to normalize the thing by the. Oh, so okay, so it doesn't have the exact same normalization. So you don't want to see some kind of.
Oh, I see your confusion. But if you just
right somewhere.
right, yeah, the data has to be prepared in a certain way. Right. It doesn't. I mean, the bright and the faint are independent. So if you're subtracting the same values from the faint, you're creating new ones.
Hindsight, that makes more sense.
Yeah. Okay, so I'm going to put the solution up for 2B. So can I just quickly ask, if you have not evaluated the accuracy, can you just do eyes on me for a second? Okay, thank you.
Was it for
Yeah, you could
the
just
bad
add
one?
that,
Or for the good one? Oh, like 66.
Yeah, and then accuracy is just,
Okay,
Oh.
so real quick, people that are trying to figure out accuracy, you can just use accuracy score, which has been imported there, and you can give the predictions and the true answer in accuracy score. That'll make it real easy. Okay? You should be good otherwise. Just,
Oh,
you just
okay.
go right there, accuracy score. Oh, and
No, that's a scribble.
yeah, one second.
From their screen.
Excuse me.
Oh yeah, maybe it's less.
You getting stuff?
Maybe we should
Yeah.
zoom in.
oh, okay, so probably there's a data type change. That's the only thing I can think of. So let's create a new cell. Let's just see what and why. I see.
Oh, okay, good.
Okay, so that, okay, and then if you do y, just work that up. Okay, so that it fell. Something about that, yes. Sorry.
Does she have the unknown problem?
There you go. Yeah, no problem.
It's just a Unicode issue. Yeah. Yeah, I was going to show you. She already had it. She had it in one cell, but not the other. Oh, okay.
All right, so, hold on a second.
All cases where training with the predicate, we want to predict on. We're not trying to predict the right source of all. So, we have the input columns, the first here. Right? Yes.
Anyone check the things for the
So then basically the training set is the right sources, and the test set is the thing. We're not putting.
What do you have, like, the accuracy to your variance?
Yeah, that's right, perfect.
That's like it has most of them are galaxies, only one is the star, and that's the projection of that.
Well, there weren't many stars in the original PSA.
Let me check. There are 6,000 are galaxies. 3,000
You can
different
just an operator, you'll see in a second, you can use something to access. That's what I did, I think it's so fast. You basically, you select the column and then you say view access, which creates that column in the shape of the thing. You can drag into it, we'll see in a second.
Okay, so we're getting close. I think we're about ready for a break. And I saw, so I believe everyone got the predictions right. So the slightly different numbers, there's some randomness in random forest, so this will happen. But the raw features produce an accuracy of about 2/3. Right? Most people were there, which is not that great, right? I mean, I can tell you, compared to just about any star galaxy model you'll find out there, that's actually quite terrible. All right, and so, okay. All right, but we can use some domain knowledge, right? Which is that we know galaxies are not modelable by a PSF. So if we normalize everything by taking the difference relative to the PSF magnitude, we'll be working in a new, essentially difference space as opposed to absolute brightness space. And we can train our model instead on those features. And some people got here, some didn't. So normalize the feature vector relative to PSF magnitudes, and then refit the nearest neighbor model and look at the accuracy then. Okay? So we'll, I think most people are here right now. We'll spend one more, if you didn't get this far yet, we'll spend one more minute working on it. And then I want to break in a couple minutes. So the main thing basically is creating this new feature vector. That's the sort of tricky thing here, right? So if you aren't done with 2C, just quickly, can I get eyes on me? Okay, thank you.
We're just dropping them. Well, PSF minus PSF is 0. So that's right. You can include that. It won't. Your model can't make a decision right here. If everything is identically 0, your model can't.
First model returns all the galaxy, all the objects. Only one of these. The first model, which is the percentage accuracy, we just assume everything.
Yeah. Wow. That's the point.
Oh, no, because I was.
And then we don't want to take the median, we want to subtract for each row, we want to subtract the value of that row.
Yeah.
You said feature change normalization without training, yes. So you mean that we should be normalizing this by the PSF max, right?
1000 by 8.
So could it be normalizing the main stars by the main PSF magnitude?
Yeah. Because if you're subtracting, right, the bright stars don't know about the main stars.
Yeah.
So if you're subtracting numbers related to the bright stars, you're creating new numbers that
Oh, the problem is.
Okay, so
It's not like it was before.
I'm sorry we didn't quite all get there, but I do think it's probably important that we take a break right now. So here's my solution. So if I could just get everyone's eyes up for a second, and if you don't have this down, you'll want to get this down because it's going to be important moving forward. So I've created 2 new arrays that I call bright x norm for normalize, faint x norm for normalize. And I just take the first column, which is the PSF magnitudes of bright x, and then I use this numpy operator, the numpy new axis, which essentially reprojects that column into an array that's the same size as bright x, selecting all columns from 1 over. Okay? So this, you maybe haven't seen this numpy operation before, so don't, this is not something to be worried about if this tripped you up. Right? We do the same thing for faint x norm. So now we've gone from a feature vector that has 8 columns to 7 because we've subtracted the PSF magnitudes from everything. Okay. And then we fit the model in the exact same way. We make predictions in the exact same way. I created a new variable name for that, which is faint pred norm. Right. And then measuring the accuracy score then, I get 91% or so. And you probably got something similar, and there's going to be some noise in there. Maybe. Okay. So I'm going to leave this up. Right? But the point here is we've just used, right, basically 2 different portions of the universe that shouldn't know anything about each other to actually, right, because the faint sources aren't necessarily going to be the same as the bright sources. But we've done just a little bit of feature engineering, right, by subtracting off the PSF magnitudes and just looking at the difference. Right? And that's essentially what we visualized as well. Right? So the stars sat on the diagonal. The difference was about 0 between the PSF magnitudes and all the other magnitude measurements. The galaxies, there was a lot more spread there. So that simple normalization has allowed us to dramatically increase the accuracy of our model. Right? And this is just one minor feature engineering thing. Right? There's many other things you could do. See my talk earlier, for examples. All right, so I'm going to leave this up. If you don't get it down now, you can get it down during the break. Let's break. It's 10:35. All right, is 25 minutes enough for coffee, people? I'm sorry, it went a little long. All right, so back here at 11. When you're back here at 11, those of you that want to work on your own, going through the notebook at this point, feel free to hop over to the tables. I'm going to do the same style thing, going through piece by piece over here if you want to stay on the lecture afterward, okay? So break back here at 11, please. Thank you.
I'll stop.
Oh yeah, we can stop.